Questions about anything from last time? Or anything? Homework due is due in GradeScope tomorrow, Thursday, at 11:30 p.m. And I guess I want to say no late papers unless you've made prior arrangements because you have some issue about the due date, just to avoid the hassle with my grader that late papers create. So be aware of that. Were there any questions? Question? I haven't said it yet. I'm thinking that it'll be around March 5th. Do you really need it's an in-class exam. Yeah. Okay, yeah, it's around, I probably will set it to be March 5th. I'll decide about that soon. Other questions? Let's say today I'm going to finish up Chapter 1 and talk about a couple exciting things. We've been saying that a lot of basic calculus goes over to the complex numbers, including things about series, for example, power series. And it turns out that understanding power series and complex variables is very important to the whole business of doing calculus with complex numbers. It's a miracle that being complex differentiable is going to mean that a function can be expanded in a power series. And that's not true in the real case in general. Some can, but not all. But in the complex case, they're very intimately connected. And it turns out if you understand the one power series, geometric series, then you can understand them all. And so I'm going to say a little bit about geometric series today using complex numbers. So there's the basic formula you probably learned in junior high somewhere. Let me review quickly how you get this basic formula. Let's call this partial sum here Sn of z. I like to call this minus that thing the nth error. And I want to know when that nth error is going to go to 0 inside the so-called radius of convergence of that power series. And I'll show that in a second. Remember, the key to doing this, getting this formula from junior high was if I multiply that partial sum by z, then let's see, that would be z plus z squared plus etc. out to z to the n plus 1. And you look at that and compare it to the line above, you realize, aha, if I subtract that from the line above, then a lot of the stuff in the middle cancels, and on the left-hand side, I get, let's see, when I subtract this, the 1 stays there, but a lot of that stuff between the n's cancels. So z squared, etc., all cancels. Z to the n even cancels, and then, but I have a minus z to the n plus 1 hanging out in the bottom line. So when I do that subtraction, it boils down to 1 minus z to the n plus 1. And so when I factor out 1 minus z in that calculation, I get 1 minus z times z to the n is z sub n 1 minus z to the n plus 1. And dividing by that 1 minus z gives me the formula that you learned in junior high. So check. And a big fact is that basic series has a radius of convergence. And this time it's a true radius. It's a radius of an actual disk. So a fact now, this is why we call it a radius of convergence. If the modulus of z is less than 1, then that series converges. Converges to 1 over 1 minus z, meaning that error term goes to 0. Okay, and to get you ready to do these basic arguments that are calculus with complex numbers, I like to introduce some words here. I call the triangle inequality a numerator estimate. And I'll explain that in a second. So a numerator estimate is the triangle inequality z plus w is less than or equal to modulus of z plus modulus of w. Yeah.
Back up at en of z that you defined.
Yeah.
Is en of z just the right side of that?
It's starting at the minus side.
Okay, starting at the minus side?
Yeah, so this is the error. The limit's going to be 1 over 1 minus c. And that junk hanging on the end there is the error. I'm going to show that error goes to 0. I need to estimate that. And I'm going to use, I like to call this a numerator estimate. It's just a triangle inequality. And a denominator estimate if something is in the denominator, usually you're wanting to show that something's less than or equal to something. And if something's in the denominator, you want it to be bigger than or equal to something to get the estimate you need. And so the estimate in the denominator is z minus w is greater than or equal to the absolute value of the modulus of z minus the modulus of w. And you can also, let's see, if I replace z, w by minus w in this thing, then I get z plus w is also greater than or equal to the modulus of z minus the modulus of w, absolute value. And you see that just by letting replace w by minus w in the first one. When you do that, then the other one pops out. So those are denominator estimates because they're greater than or equal to. And so, for example, if I were going to apply this concept, I'd have a quotient like a plus b over c plus d. These are complex numbers. If I want to estimate that, in the numerator, I'd use the triangle inequality. But in the denominator, I'd use this other inequality. And hopefully I'll get something. And that's exactly what I'm going to do here. So the proof of that fact let's see. So I have the partial sum out to n minus what I expect to be the limit. That's equal to the modulus of minus z to the n plus 1 over 1 minus z. And that's going to be less than or equal to, let's see on the top, I'll have a z to the n plus 1. That's going to be the key. That's going to go to 0 nicely when mod z is less than 1. But on the bottom, I would have a 1 minus the modulus of z absolute value. And a key here is that if the modulus of z is less than 1, then that absolute value is equal to 1 minus the modulus of z. Because that's 1 minus the modulus of z would be positive. And so I have that this thing right here is less than or equal to, maybe I'll, since I'm doing steps here, I'll put z to the n plus 1 modulus on the top. And here I would get, and that's equal to the modulus of z to the n plus 1 over 1 minus mod z. So that thing is actually equal to that. When it's important to say, the modulus of z is less than 1. Okay, so I use the denominator estimate there. And that goes to 0. As n goes to infinity. So sure enough, that geometric series converges when the modulus of z is less than 1. Okay. I should maybe continue to say when mod z is less than 1. A basic fact, calculus fact, C to C, that's the same as R to R, and the proof is exactly the same. If a series of complex numbers converges, then the terms have to go to 0. If a series converges, the terms have to go to 0. As n goes to infinity. And that's exactly the same proof that you'll find in your calculus book. Very elementary. Okay, maybe I'll underline this. So consequently, let's look at the case where mod z is bigger than or equal to 1. Consequently, if mod z is bigger than or equal to 1, that geometric series does not converge. Because the terms don't go to 0. Since the modulus of z to the n is the modulus of z to the n, and that's going to be greater than or equal to 1 to the n, 1, period. That shows that those terms don't go to 0. So they can't possibly converge. So the terms do not tend to 0 as n goes to infinity. Okay? And so that's a true radius of convergence. I get convergence inside and divergence outside. On the actual circle, well, that's an iffy thing. Very often we'll have to think carefully what happens on the actual circle of when we're talking about it, a disk of convergence. So on the boundary of that disk, subtle things can happen. That's basically where Fourier series live, and they're subtle. Questions about that? Well, it's a mind-blowing thing, or rather surprising, that understanding that series is the key to understanding all complex series. And we'll see that very soon. I thought this would be a good moment to take some time to do something really interesting, to talk about the power of the complex exponential and the de Moivre formula. So remember, de Moivre's formula is that e to the I theta to the nth power. Let me make a little n here. Is e to the I n theta, and that's cosine n theta plus I sine n theta. And that holds true for integers n. Well, there's some famous formulas that fall out of this. Let's see. So we have e to the I theta is cosine theta plus I sine theta. We have e to the minus I theta is, well, cosine minus theta is cosine theta. Sine minus theta is minus sine of theta. And Euler looked at that for about, in his case, probably seconds, and realized if I add those two together, the sine thetas cancel, and I get, so I'll put a plus here. When I add them together, I get e to the I theta plus e to the minus I theta is 2 cosine theta. So the famous formulas, let's see, I'm going to get two famous formulas. The first one is cosine theta equals e to the I theta minus e plus e to the minus I theta over 2. And if I subtract those two formulas, I'll get 2I sine theta equals something. And so when I divide by 2 sine to the 2I, I would get the formula sine of theta equals e to the I theta minus e to the minus I theta. That would be equal to 2I sine theta when I subtract. And so now when I divide by this, when I divide by 2I, I get sine theta. So that's the same thing when you get using minus above instead of plus. Those are pretty interesting. Those are the cosine and the sine for real angles. And when we get later on, we're going to want to have cosine and sine for any old angle, complex numbers. So later, in fact soon, we'll let theta be in the complex number and use these formulas to define the sine and the cosine of a complex angle. Cosine, sine for angles. They're not angles anymore in the complex plane. It's going to be natural and inevitable. Questions about anything? Well, this is one of my favorite things to do with this material. I call this a very famous Fourier series fact. Anybody in here taking both my classes? I'm also okay. Well, so this is a famous Fourier series fact. I'll be talking about this also in that class. Oh, maybe I'll do it. Let's see, a famous Fourier series fact is this is a Dirichlet kernel that comes up when you analyze Fourier series. It's 1 plus cosine theta plus cosine 2 theta plus etc. Cosine n theta. That looks like it could be something horrifically complicated because those things are all wiggling at different rates. And cosine n theta is a very fast wiggling thing. Well, it turns out this has a very simple expression of sine n plus a half theta over 2 times sine theta over 2. That's the so-called Dirichlet kernel. And if you understand the Dirichlet kernel, you understand Fourier series and convergence. It's called dn of theta. Well, I won't demonstrate that exact thing. What I will demonstrate is that 1/2 kind of makes it less fun to talk about. It's slightly more complicated, and it takes more work to get that formula there. But if I had 1 in place of 1/2, then this would be an easier thing to talk about. So that's what I'll do. Yeah.
I assume for sine n plus a half theta, that's all inside of the sine.
Yes. Yeah, if I wanted to be clear about that, I'd put a bracket here. You realize when you look at that for a second, or maybe a minute, that that's the real part of a complex number. Namely, by de Moivre's formula, well, this is just Euler's identity. 1 is real, so I stick that there. Cosine theta is the real part of e to the I theta. Plus, plus, cosine n theta is the real part of I n theta. Okay, that's cool. And this is a geometric series in disguise. This is 1 plus e to the I theta. E to the I2 theta would be e to the I theta squared. And e to the I n theta is e to the I theta to the n. That's the de Moivre formula. And we just got a formula for the sum of a geometric series. This, the red part, is, let's see, what is it? 1 minus e to the I theta to the n plus 1 on top over 1 minus e to the I theta. And you look at that for a little bit and realize, let's see, I kind of wish that thing on the bottom was a real number. Then it'd be very easy to figure out a formula for that. And you realize, oh, it kind of looks like a sine theta. So in fact, I'm going to multiply the top and the bottom by, let's see, I'm going to multiply the top and the bottom by minus e to the I theta over 2. And let's see, why don't I make it divided by 2i? So I'm multiplying by 1 here. Then, on the bottom, this is why I'm doing it. On the bottom, I get e to the I theta over 2 minus e to the minus I theta over 2 divided by 2i. That is the sine of theta over 2. So I could write out now that thing on top, but this thing on the bottom is sine theta over 2, which is a real number. And so it would be fairly easy to figure out the real part of the thing on top. And so the answer, I don't really care what the answer is. all I care is that actually I could find it, and it would be relatively simple, and it would be a finite, simple thing. It wouldn't be a sum anymore. And that's the fantastic breakthrough of the formula for the Dirichlet kernel. So this would be equal to the real part of the squiggle, whatever that is, which wouldn't be complicated. I just don't feel like writing it down, over sine theta over 2. So how's that for a powerful thing? From complex numbers. This is a fact about a real sum. And I use complex numbers to get it in a rather straightforward manner. So clean and easy formula. Clean, simple formula. And putting a 1/2 instead of a 1 there turns out to make it cleaner and simpler. This one would be slightly messier, but certainly within our reach. Questions about that? Let's see. You might have noticed that I didn't give you any homework problems from section 1.7. That is just a thing that we're going to be using as a sort of a language in the complex plane. It's a fascinating thing to think about. In the real numbers, there's a plus and there's a minus infinity. It's traditional in the complex realm to think of the point at infinity. And I'll explain how we feel about the point at infinity. I guess I'll put in quotes at the moment. The point at infinity. So let's see, in the real numbers, we'd have a plus infinity sticking out that way and a minus infinity sticking out that way. Okay. In C, the feeling is going to be, here's C, the complex plane, the real axis, the imaginary axis. If you're going to point at the point at infinity, everywhere you point is pointing to the point at infinity. And I'll explain how you could possibly think that way. Let's see, there'd be arrows on the axes also. It's a lot of infinities. And it's going to be useful when we talk about a type of blowing up for complex functions. So the definition here is limit as z tends to a of f of z is equal to the point at infinity is going to mean that the modulus of f of z goes to plus infinity in the real sense as z tends to a. Or more precisely, let me say, in the mathematical sense, what that means. Given a real number m bigger than 0, there is a delta bigger than 0 such that f of z is bigger than m when the modulus of z minus a is less than delta, and z, of course, can't be equal to a. That's where it blows up. So, simple examples of things that do that kind of blowing up. guess the simplest example is 1 over z minus a. But powers of z minus a in the denominator also would have that behavior. So, for example, z minus a cubed is also the point at infinity in this sense. Okay, that's a formal definition. You don't have to have any feelings about it. It's just a formal definition. But people who study these things forever, like me, get a feeling about it. And the feeling was introduced by Riemann when he talked about something called the Riemann sphere. Well, the Riemann sphere. My Riemann sphere is going to be slightly different than the question. Yeah. I meant to do it twice here. I like my Riemann sphere to be sitting on top of the complex plane. The book has it wallowing in the complex plane. So let's see. This is my complex plane, this green thing. And I like my Riemann sphere to be sitting at the origin, like that. And then if it's sitting at the origin, then I think of this as the North Pole. And the North Pole is going to correspond to the point at infinity. Okay. And I'm going to identify this sphere. It's a ball sitting on the complex plane. So this green thing is the complex plane. I'm going to do stereographic projection. So I take a line segment that pokes through the sphere, pokes out right there, and comes out and hits a point in the complex plane, Z. That's called stereographic projection. And this, I'll call this a Z prime. Z prime is on the sphere, and Z is in the complex plane. Z prime is in the sphere. Call that blue thing the sphere. Well, that sets up a one-to-one correspondence between points in the plane and points on the sphere. And every single point on the sphere gets hit, except, of course, the North Pole. The origin would be the line that goes straight down, North Pole to South Pole. And every point in the complex plane gets hit. And the whole sphere gets used in that, except the North Pole. The North Pole doesn't map out to anything. And if you think about a little Arctic circle up here, let me make a purple Arctic circle. Here's a little Arctic cap. If you think about where that polar cap goes, that would go to the outside of a gigantic circle. And the smaller that cap, the farther out that circle is. And so the feeling is, when I add that abstract point to the complex plane, it compactifies the complex plane and makes it a sphere, which is a compact set in the mathematical sense. Every open cover has a finite subcover. Okay. So the language of math is that minus infinity to infinity compactifies the real line. It's a two-point compactification. But when I take C union this abstract point at infinity is the one-point compactification of the complex plane. And this is used so often that we call this the extended complex plane, C hat. You add one abstract point to it. Okay, so it's an abstract point. You add it in. And if you're going to talk about now topology and that kind of thing, that polar cap you think of as a little neighborhood of the North Pole in the sense of topology. A little, in fact, I like to think about it as a disk. This is my my notation. A disk of radius epsilon about the point at infinity is that polar cap. And let's see, what would that be? That would be the set of z in the complex plane. I like to make the modulus of z bigger than, if epsilon's small, then 1 over epsilon would be big. Union, the abstract point. Okay, that's that orange, that purple shaded stuff outside of a big disk. Would give me a little tiny polar cap. I think of that as a small neighborhood about the point at infinity, or a small disk. In topology, disks are called balls, even when they're disks, or disk, about the point at infinity. Okay, so it's just a language we use, and it wouldn't be a useful tool were it not for that behavior of 1 over z minus a. It blows up in just the right way to make this a reasonable thing to talk about. And that's why we do it. So it takes a while for this to feel natural and reasonable, but the more I say it, the more likely that will be to happen. Let's see. Okay, that finishes off chapter 1. I didn't give you any exercises about this. I just wanted you to read that and be aware of the words. Question?
I guess I'm a little confused about, so the union with those lines, is that, you're calling it one-point compactification, is it not a disk of infinite, like literally a circle of infinite radius in the set of all points?
Right. Oh, the feeling would be that I'm taking the complex plane and wadding it up and sticking it together at the North Pole. And that all that stuff that's way far out in the purple shaded region gets squished down to a little tiny polar cap. Okay. And so in topology, things are, you can deform them in continuous ways. That's how I would deform the complex plane into something that I can just add one abstract point and make it basically a sphere. So I'm like doing wallpaper. But of course, I have to squish the far out stuff to jam it down to the polar cap. Yeah.
So it seems like the sphere's like finite surface area?
Yes, so that's the thing about being compact. It has a very finite feel.
But it's like very dense, basically.
Right.
Like, okay.
So by sticking in that abstract point and using that topology, you turn the complex plane into a very concrete thing. And Riemann did a mind-blowing thing. He kind of invented the concept of a manifold. He turned that into the first complex manifold. And that turned out to be a really brilliant idea that led to all kinds of important math. Studying algebraic geometry, polynomials, anything, Riemann surfaces come up. And this is the first Riemann surface. Let's see, so next time is a big lecture. I'm going to talk about the Cauchy-Riemann equations. And last time, let's see, maybe coming soon. The Cauchy-Riemann equations. So far, everything we did felt like doing calculus with complex numbers in place of real numbers. Suddenly that's going to change next time. There'll be a different feeling about complex differentiable functions. So let's see. So example, z squared was differentiable. The difference quotient for z squared was z squared minus a squared over z minus a equals z plus a, when you factor it and do the usual thing from freshman calculus. And as z tends to a, that tends to 2a. And when you think about it, if you're making the estimates, you're looking at, here's a. That difference quotient tends to 2a no matter how you come at it. And I would get estimates that work from any conceivable direction there. Okay, and last time I showed you this example, z bar. And the difference quotient, well, let's see. Let me do z bar minus a bar over z minus a. If I write z equals a plus something tiny, r e to the I theta. So that would be a plus something. I'm thinking of r as small. I could describe that points in the disk, the orange stuff, by that. And when I do that, that difference becomes, let's see, I did it last time. That would be r e to the I theta conjugate over r e to the I theta. The r's cancel out, and I'm left with e to the minus 2I theta. I did this calculation when a was 0 last time. And the annoying thing is that that's different along all radial directions. So z tends to a when r tends to 0. And so I get different limits coming in different radial directions. Along different radial directions. That means that limit doesn't exist in the complex sense. The limit as z tends to a of the difference quotient does not exist. So z bar is not complex differentiable. At any point. Last time I showed you it wasn't complex differentiable at 0. This time I showed you it doesn't happen at any point. Okay. Well, it turns out that if you want to show that something is complex differentiable, you don't have to check all directions. You only have to check 2. And that's the Cauchy-Riemann equations. let's write f of x plus iy is equal to u of xy plus iv of xy. We're going to calculate the difference quotient. And of course, if it is complex differentiable, then when we do this, let's see my picture here. I'll have A right here. I'll be inside some disk. It turns out that I only need to check these limits if I'm coming in from a horizontal direction and a vertical direction. Okay, so if the difference quotient exists, if f prime exists, then those limits, the orange limits and the purple limits, would have to agree. And it's going to be an exciting thing that that's all you have to check. If they do agree, then the thing is going to be complex differentiable. If f prime exists, the horizontal limits and the vertical limits exist and are the same. And of course, Riemann and Cauchy realized that it turns out that if those are the same, then the thing is complex differentiable. So the exciting fact the reverse is true. Of course, we'll need some assumptions. We'll need f to be sufficiently differentiable, and I'll talk about that next time. So there's going to be two parts of this theorem. One is going to be to show that if f prime exists, the Cauchy-Riemann equations hold. And then the second part is going to be the reverse. If the Cauchy-Riemann equations hold, the thing is complex differentiable. Since I have 2 more minutes, I might as well write down what the equations are. This might be the last time I write Cauchy-Riemann equations. I like to write CR equations. Here they are. du dx, that turns out to be I'm going to get one of these from going in horizontal and the other from going in vertical. And one of them is going to be du dx equals dv dy. Or that was the u plus iv that f is. And the other one is du dy equals minus dv dx. It's very easy to check that the z bar thing does not satisfy that. But the z squared one, real and imaginary parts, do. So if I write z bar, that would be x minus iy. Let's see, I'll write. That's x plus iy bar. That's x minus iy. We see that u of x is x. U of xy is x. And we see that v of xy is minus y. That doesn't satisfy those equations. And so